Morning, everyone. Today I want to talk about dynamic programming versus using backtracking algorithm to solve the 0-1 knapsack problem. When I did this, I kind of wanted to use the book pseudocode so I can get more familiar with how they format their pseudocode, which is obviously it's C style, but it's not exact, of course, it's pseudocode. So I wanted to kind of look at that, and also a lot of the stuff I found on the internet was just plain not what I wanted to find. I would look for backtracking algorithms, and I almost always found dynamic programming algorithms, and it was very irritating. So I was like, no, what? I'm just going to look at the book and see what they do and kind of base some code off of that. So, but to get to the problem here, backtracking algorithm is a way of solving a problem by using essentially a depth first search tree. You start at the root and you keep going to each child, each descendant, and you keep doing that. And each time you see if that particular node is promising, if it's likely to produce a optimal solution. If it's not promising, it means it's not going to have any way of producing that. So you start backtracking and you backtrack up to the parent, and you keep doing this over and over, and eventually you kind of weed out the nodes that are not part of the solution. And it has some advantages over dynamic programming in certain situations. Sometimes dynamic programming is better. It just depends. In dynamic programming, remember, we're keeping track of every sub-problem as we go, so we're not re-solving the same sub-problem. So it does have more memory requirements for dynamic programming. And but anyways, kind of want to get into my code a little bit on this one. I kind of want to keep this a little bit shorter than my other videos. So let's go. I want to look at first. This is just my initial code. This is me translating. I don't know why I took this out of the code. Thinks it's not used, but it is. I guess I'm not really using it actually. I'm actually using it. Anyway, getting off track here. This is just basically the code I translated from the pseudocode in the book. Notice I'm going to call these global. They're not global variables, but they are fields of the class. And that means whenever you run this, it's storing everything in this in the object you instantiate. So in order to use these methods, you would have to instantiate a new object every time, yada yada yada. But for this just simple translation, I'm just doing what the book uses, and it's all pretty straightforward. I'm not going to go over all this code. It's really straight out of the book. It's almost identical. The only real change I had to make was the book uses one-based indexes, or indices, however you want to pronounce that, one-based indexes, and I use C# is zero-based. So it was kind of funny. I knew that, so I counted for that, and everything I did, except for one little part, when you actually call the very first, this is a recursive algorithm, so it's a recursive method. But when you first call it the first time, you have to actually, they passed in 0, and I didn't catch that until I looked at it closer, and I was like, oh wait, they're passing in 0 and they're one-based. Let me pass in -1. Oh, that fixes everything. So anyways, just fun little things while translating their pseudocode, but nothing too exciting there. But let's switch over to my actual code. Okay, here's my actual code. And if you will look at all I did, I just kind of converted it to my way of doing things, or to kind of fit in with my program. Instead of keeping variables stored at the class level in fields, we're passing everything around in in the method calls, function calls, and storing them in local variables. It allows me to have the methods being static, so you don't have to instantiate an object. There's no real need to for these kind of methods. But here, this is all my backtracking code. It just has, the recursive algorithm, and which is called from this initial method. And we have the promising. This is where the fun stuff really happens. But I'm not going to go into all this detail. I just kind of want to show my code real quick. I want to get to the actual test results. And I'm not even going to run it. I'm not going to show you how I run it. It looks very similar to the way I did my last one. So I'm not going to waste your time looking at how the program looks and everything. But I will say this. I changed one thing from my last project to this one. I added in 3 new tests, and there's a reason for that. As you can see right here, this is just like in my previous project. We have a constant capacity of 1,000 items, and we're increasing the item count from, I think it's 100 to 10,000. And as you can see, we're not, dynamic performs more slowly than either backtracking or greedy. In fact, greedy and backtracking perform almost the same. They're neck and neck. But dynamic performs kind of similar to the results I got in the last one. Still has that same little hiccup right there, as it always did. But very similar results. And it looks like backtracking is performing very well. Test 2, same thing. This one here, we have a constant item count, but instead we're incrementing the weight range from 100 to 10,000. And as you can see, kind of similar results from the previous report. Dynamic is performing as expected, and backtracking and greedy are both performing very similarly. And you'll still see greedy is not 100% on its on finding the optimal solution, but it's pretty close. Now let's add a little wrinkle to this. I didn't like this because I knew that the backtracking algorithm will not perform the best in every case, and there will be scenarios where it should perform worse. So how can I incorporate that in there? Well, there's actually, if you do some search for it, there's some ideas on that, how to come up with basically worst case scenario. I don't know why I keep drawing here. Worst case scenarios, that kind of thing. But I just wanted to kind of use my random number generator like I've been using. But what I did, I tested this with a constant item count of 1,000 and a constant weight capacity of 1,000. But now when I'm generating my random number input, where I'm giving a random number for the value, random number for the weight, I've changed it up here. I'm now changing the range of values that are possible. And I don't know why. Yeah. So anyways, and there's a few ways I could do this. I could just keep increasing the minimum until it equals close to the max, or I could just decrease the maximum to increase close to the minimum, and that gives you a smaller range. But I thought it'd be more fun, and actually it ends up giving more interesting results, to shrink it on both sides. So every iteration, we increase the minimum value for random number generation by 10, and we decrease the maximum value by 10. So for this particular chart here, we're looking at a run where, or this test here, we're looking at a run where the item count is 1,000, weight capacity is 1,000, weight range was 0 to 1,000, and our value range changed over time. So the weight range was a constant. It was always 1,000 max with a 0 minimum, or 1,000 max with a 0 minimum. That's for the random number. It could be anywhere in that range. The value range, however, kept changing. At the start, it had a range of 1,000 possible values. By the end, there was only 20 possible values. And it did this, like I said, by increasing on both ends. So you start off at 0 to 1,000. The next one would be 10 to 990. and you end up with what, 490 to 510 as the range. So a very small range right in the middle. And as you can see, as you start getting to higher value, it's random, so it's not going to always be a nice, perfect little, progressive linear type look. There's randomness to it. But as you can see, as you start getting to smaller ranges, backtracking starts having some trouble. It starts hitting some sets of data that really slow it down, and that's kind of interesting to see. Whereas, relatively speaking, the other ones don't really care. Greedy and dynamic, they don't care. They don't care about what kind of values are getting thrown in there on this. Now, from my understanding, the dynamic algorithm actually should have some worst case scenarios that will make it perform worse. I'm not really trying to hit on that. I didn't really hit that, obviously. I need to explore that more to figure out how to hit the worst case scenarios for dynamic. But as you can see, backtracking is clearly having some trouble here. So on this one, like I said, the range was kept constant, but the value range was changed. Test 4, we do this a little different. We keep the value range constant, so it's just like it was in previous tests, not counting test 3. And we change the range of the weight. We do the same thing, increase the minimum, decrease the maximum each iteration. And kind of has the same effect, has a few little hiccups here and there, and it starts getting, some slowdowns and stuff, but does some interesting things. If you've run this multiple times, you'll see more and more like slowdowns as you up here, but it's random. You have to run multiple tests with each time with different sets of random data, and it starts getting kind of unwieldy to manage all the different tests and everything to give like averages or things like that. It starts getting a crazy amount of loops, and the code gets convoluted, and it's just hard to follow. Now here in test 3, we combine it. We have a constant count, constant weight capacity, and we are decreasing the value range and the weight range. So they're both changing. So as you can see, when you change them both, you really start seeing an effect on the performance of backtracking. So what's the takeaway from this? And kind of the book hits on this, and I have to agree that backtracking can perform better than dynamic. On average, with most data, according to the authors of the book, it does tend to perform slightly better, but there are worst case scenarios and worst case situations where it will perform worse than dynamic. So yeah, it really depends on the type of data you're using, on which one is better. I know the book mentions you can combine, there's algorithms that combine divide and conquer with dynamic that work really well for the knapsack problem. But there's a lot of ways to solve it, and it's really fun to look at all these different ways. But I think I will stop there, keep this one a little shorter than usual, and not waste everybody's time. So I hope everybody has a great day, and good luck in your coding.